This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
Okay, so today is lecture number 4, and a few main things for this lecture. First, to review a little bit about intersection of Bezier curves or curves in general, how to do that, and then 2 other topics that I will start today. And one topic is called change of basis functions, representing the same curve in different bases, and the other topic is called degree elevation, going from a curve that is of degree n to a curve that is of degree n plus 1. So the first part will be still review of the intersection algorithm we discussed last time. And the problem that you have to solve also as part of your first programming project is the problem of figuring out where 2 curves intersect. And on a very high level, you don't have to copy this from the board, you already have it in your notes. The problem is if the curves are too complicated, or if I do not want to solve the problem by setting the 2 equations, defining these curves equal, and solve it that way, what can I do? I can try to make the problem simpler. And the way I make it simpler in this class is by taking a complicated curve and cutting it or splitting it into 2 pieces, and then you look at the individual pieces, right? That's the overall idea. So in order to resolve this, we do not intersect or try to intersect the original curves, but we take the first curve from here to here, and we cut it into 2 chunks. We take the other curve, the second curve, and also we think it's too complicated, we cannot deal with it right away, so we split it into 2 chunks. And now we can iterate that, right? And split all the child curves again into 2 children each, and now we have a bunch of smaller curve segments, which we will treat as individual curves in their own right, and figure out where is the intersection. Ultimately, if you do this, the question becomes, how can I use a very effective means for intersecting, meaning the intersection of boxes, to figure out where 2 of these segments possibly intersect, right? You reduce the exact problem of finding intersections by solving roots. I mean, don't want to do that. You don't want to find roots or approximate roots or use an iteration scheme to find roots. You just want to use bounding boxes. So the essential idea is you look at the bounding box of something and you say, this bounding box doesn't intersect at all with the bounding box for that piece or that segment. Therefore, I can eliminate these pieces from the whole consideration. That's the overall strategy. And what is left in this particular case is that, well, indeed, a bounding box for this part of the curve number 1 and the bounding box for this part of curve number 2, they do indeed intersect. Here, the bounding boxes do. So you kind of have a rough idea where the curves intersect. They may or may not intersect. Okay, that is still unresolved. But these boxes will ultimately get smaller and smaller and smaller. And you say that's small enough, I consider them as being of the intersection type. That's the overall idea. And the way we do that for Bezier curves, so was use bounding box tests, right? Bounding box BB test to approximate. We just approximate them to approximate intersection points. And on the highest level of abstraction, you say 2 Bezier points, 2 Bezier curves intersect or are assumed to be intersecting if their two control polygon bounding boxes do intersect, if their two control polygon BBs, bounding boxes, intersect, and, this is very important, and these two bounding boxes are very, very small. And the two bounding boxes, BBs, are very small. So you have to define what that is, very small, very small. Okay. So the idea was I have a first Bezier control polygon, this polygon, the other control points. I don't even deal with the curve. I don't care about the curve. I only care about the bounding box of this first control polygon. And then I have somewhere I have a second curve, and the second curve is here. Control point, and control point. So its polygon looks like this. So its bounding box is this one. Okay. You don't draw the curves. You don't compute anything on the curves. All you do is based on these bounding boxes. Okay, and these two bounding boxes intersect because x max of the first bounding box is larger than x min of the second bounding box, right? And y min of the first box is smaller than y max of the second. And so there's conditions. You can easily figure out when the boxes overlap, right? You can do that. So now you say these two curves intersect. There's an intersection point. You don't compute it, but you just say there's an intersection point where it is somewhere in the union of these two boxes, right? Right? So if I were to draw the curve, well, the curve here, curve number 1 is this guy, curve number 2 is this guy. So the exact intersection point is here. You see it with your eyes, right? That's where it is. The machine or the computer doesn't have to compute it. Okay? I only say the intersection point, there is an intersection point somewhere in the union of these two rectangular regions. That's it. And you also want to make sure that these boxes at this point of decision making are very, very small. You can say each of these boxes, if you use screen space as an example, each of these boxes occupies less than a pixel, for example. If that's your criterion, right? Then your eye will not be able to see any further. But it can be another parameter too. But again, they may or they may not intersect. Right? The two boxes can overlap, but the curves do not necessarily have to intersect. They are just very, very close. So if the boxes are very small and they do overlap, that means that either the curves do intersect or that the two curves are very, very close. And you call that intersection. That's what you do. So if you have this particular configuration, for example, curve number 1 and the curve number 2, and you have control polygons for these curves, then what you will see in the end, you will not get the exact point of these intersection points, but what you will get is, you will get, for each of these intersection points, two boxes, two very, very small boxes, bounding boxes of local control polygons that overlap. Okay, so there will be a bunch of little bounding boxes that you can compute for the local subdivided curve, and here will be one part where a bounding box of the first curve intersects with a bounding box of a segment of the second curve. And you will say, well, there is an intersection point, maybe or maybe not, in that region. And you will similarly have a little bounding box here, another bounding box there, and they do overlap, and you just say there is an intersection point. And same here, you will have a bounding box for some polygon here, and another bounding box for some polygon there, and the boxes overlap, therefore you just say there is an intersection point, period. Okay, and you will get them all. Using this decider, this way to decide it, you will find all areas in which an intersection point possibly exists. Of course, this method will not be numerically good enough to handle situations like these, right? You have curve number 1, and here's curve number 2. Huh? If this is very, very small a gap, this test will probably say they intersect, even though they do not intersect, right? The other difficult problem is, of course, when they just touch, okay, there is a contact point, right? These are the general cases when it becomes very, very difficult to decide, no matter what technique you use. Does this make sense to everyone, how to play this game? And the essential technique to do this was based on taking a big curve and one big polygon and refining it or subdividing it by taking one polygon and making two out of it, right? One curve and two segments from it. That was very simple. Now, what is the most fundamental or most important algorithm that I talked about so far in class? That word and that algorithm came up over and over again, right? De Castillo algorithm. There's this beautiful geometry for it, right? This polygon and the curve and this beautiful algorithm to take ratios, 1 minus t to t and so forth. Beautiful. So it's very important to fully understand that algorithm and appreciate it. Now the question with any algorithm is this the best algorithm? Is this the fastest algorithm, right? I think in computer science we have the speed, right? Well, is this the fastest algorithm? In the context of evaluating points on the curve, what is the expensive operation in that? There was this double loop, right? For all the columns in this scheme do, compute all the entries in the rows, right? So if I started with 10 points in the first column, then 10, 9, 8, 7, 6, at the end there's 1 point, right? That was a triangular scheme. Is that expensive? What operation do you count when you want to decide on expense? The multiplication is the important, right? It always was 1 minus t times something plus t times something else. And the expensive operation is the multiplier, right? The multiplication operator. So we have to count how many multiplications there are. Okay, so this is the cost, right, or complexity. Cost of De Castillo algorithm. And we only want to count the number of multiplications at this point. Shoot, yeah, that was the question. Shoot.
So it's a triangular scheme. Can you just say the complexity is proportional to the area of the triangle?
Yes, yeah. Probably there is a square there, right? Mm-hmm. But we will count it, right? I put an example, maybe you see that. Number of multiplications. Right, that's the condition. So, for example, if we do B00, B10, B20, B30, so this is an example for n equals 3, right? Then there was a first operator, it was times 1 minus t. The second number gets times t, and then we add it up, and that gives the next number, B01. We combine these two, add it up, times 1 minus t, and this one times t, and the result is B11, and so forth. And here is B21, and then we combine two numbers here, we get B02, here we get B12, and last multiplication step is here, B03. Okay, so how many operations did we do here? How many did we here? How many did we here? N is 3, right? N is 3. In the first step we have 3 of these. Okay, so that's N. N, 1, 2, 3. N is 3, but for each combination we have 2 multiplications, right? So it is N times 2. 2N in the first step. 2N plus, how many multiplications did we do here? This is 1, 2, 3. Here it was 1, 2 times 2 each. So it is 2 times n minus 1, right? So this is 2 times n minus 1. And then for the general case, there's a bunch of other additions there. And in the last step, you only have to do one final linear interpolation requiring 2 multiplications, right? 2 times 1. So that is 2 times 1. Okay. So now we have to sum this up. What is the sum? Obviously here this is 2 times sum from I equals 1 up to n, right? So this is just 2 times sum I from 1 to n of I. And you know what that is, right? Remember that? This is just 2 times, you build pairs here of numbers, right? And so the pairs, each pair has a value of n plus 1. How many pairs can you build? N half, right? N over 2. So it is times n over 2 times n plus 1. You remember that formula, right? Okay, so when you multiply that out, then the 2 goes away, and you have, well, it's n squared plus n multiplications. So therefore, you were right. It's related to, right, there's this triangle and area of triangle. Well, this is a discrete version of that, right? So it has to do with the number of columns here, in a sense. So it's order of n squared in the number of multiplications, right? It's n squared plus n. But the highest degree occurring here is square, so it's of quadratic complexity. Is this good or is this bad? It's pretty good. Quadratic complexity, right? Can you do better? Can you do better? Well, if he is asking this question in this way, of course, then there must be a better way, right? Otherwise, why would I ask? Is this important? How many multiplications you have? Or isn't your processor fast enough? Dumb question. You always want the fastest answer, right? So, well, if n is small, like here, I mean, n is 3, so that is 3 squared, that is 9. It's not a lot of multiplications. But if you only go to 10, when it's 10, n equals 10, you have 100 multiplication, right? It goes up quickly. So, particularly when you are dealing with curves that are of higher degree, where n is large, okay? When n is large, say above 5, above 6, then yes, you should worry about that. When you only deal with curves where n is very small, 1, 2, 3, 4, then maybe you don't have to worry about it. You want to get real time, right? Whatever your application is, you would like to get the fast response. So, how can we speed this up? Speeding things up. So the optimal number of multiplications is what? Let's go back to a polynomial of degree n in so-called monomial form. These Bezier curves we looked at are also all polynomial curves. They are polynomial and the highest degree is n. But then there are these monomial forms. What are they? So to remember, if I give you a curve in monomial form, f of t, then I write it like this. I just do the example, n equals 3. Okay. I think it's always better to see the general principle by looking at the next concrete example, and then the general principle is for the computer, and the computer can deal with arbitrary numbers, right? But we like to see it for specific numbers. At least that's the way I feel about it. So look at an example, n equals 3. So the monomial form representation looks like this. It looks like C0 plus C1 times t plus C2 times t squared plus C3 times t cubed. Okay? This is called monomial form because these powers of t are the monoms, right? The monomials. Here is t to the zeros, t to the first, t to the second, t to the cube, right? It's a different basis. The basis for that Bezier curve was the Bernstein basis. Here we have the monomial basis. Okay, how many multiplications do I have to do? How many multiplications are here when I want to evaluate that? How many? Here's one, right? How many are here? 2, and how many are here? Okay. So you think it is also of quadratic complexity, right? But I give you a trick, and I tell you it is just of order n. How do you do that? By writing it in a specific way. So this is C0, right? Plus t times. I take t out. I pull it out, so it's t times something times C1 plus C2 times t plus C3 times t squared. Okay? And now I iterate the process. I pull t out of the rest. I just pull t out from all the powers of t, put it in the front, and then reduce the power of t in the interior. And now I do that in that interior expression again. Okay, so I can iterate that. So that is C0 plus t times C1 plus, I take t out, t times C2 plus C3 times t. That's it. So how many multiplications are there? How many do we have now? We have 3, right? We have 3 multiplications. Here is 1, 2, here is the third. Okay? This example said n equals 3, and you have 3, so probably by induction, right, you can see that it's always n multiplications. Can you do better than that? Is it possible to further reduce the complexity below order n? Is this the best? So if you do this bracketing differently, then you get order n complexity. So order n complexity in terms of multiplications, operations. Okay. So now comes the part where I talk a little bit about how to transform the basis from a Bernstein basis to a monomial basis, but only for the sake of speeding things up. The way we like to look at all this stuff, the Bezier world, Bezier curves and so forth, is always with the geometry. The geometry is beautiful. We understand everything very simply by looking at the geometry. But when it comes to a very time-critical implementation, then you also have to worry about speed, right? And when it comes to really getting everything out of the algorithm you can possibly get out of it, then you have to give up some of the beauty of the geometry. So now I have to talk how to get from the Bernstein basis to the monomial basis, right? So if you need an ultra-speed implementation, you can translate from the Bezier control points, the BIs, to these control points or coefficients, right? How do we do that? And that has to do with change of basis, and you had that in linear algebra, I believe.
The Bernstein one, O of n, if you just did it parallel.
One more time.
Can you make the de Cassagiu one, O of n, if it was in parallel? If you just do each one of those.
You have an idea how you can also reduce the number of multiplications in that scheme?
So like if you could do all those multiplications in parallel, then it would be 1, 2, 3, 6, 8 of them.
Well, you still have to count. Good idea. Good idea. Yes, you could devise a parallel processor that is tailored to doing certain operations in parallel, right? You can do all the steps that happen in one of these columns in parallel. They're independent from each other, right? They are independent. So therefore, if you have an architecture that supports, right, parallel processing, you can do that, yes. Then you get each response from one column to the next one at the same time. So then it's just n columns, right? You can, at some point you come to a limit. You can only do so many in parallel, right? So, good point. So if you want to do that and parallelize some of these algorithms, by all means, go ahead and do that. Okay. Those of you who play around with graphics cards and that kind of thing. The basic principle that we need is change of basis. Need to change basis, change from Bernstein basis, Bernstein to monomial basis, to be able to evaluate in order n time, to be able to evaluate, I just say in ON, okay? So, change of basis. And I just do an example again. Change of basis. Example, I use n equals 2. I first give you the definition of the curve. T, 0, 1, B0, B2, n is 2. I give you the definition of the curve, the same curve, twofold. First, in the Bernstein basis, and second, in the monomial basis. So, we know that the curve of t is sum I from 0 to 2 bi 2 of t. I can write this differently. Okay, now I write this in matrix form. I'm just trying to be clever here. So I write the sum as a matrix operation where I put all the Bezier points in one row. So this is B0, B1, B2. That is a matrix with 3 entries times the Bernstein polynomials. So I have to write that as a column. So that is B0, 2, this would be B1, 2, this would be B2, 2 of t. Okay, now I can spell them out, those polynomials. This is B0, B1, B2 times, I go back to the definition of these guys, and when you look that up, you will remember that this was 1 minus t squared. The next one was 2 times 1 minus t times t, and the last one was t squared. Now I can further multiply that out. Why do I multiply it out? Because I want to come back to the monomial basis. So if I multiply it out, I come to B0, B1, B2. And now I also write this column vector as a product. And the product would be 1, minus 2, 1, 0, 2, minus 2, and 0, 0, 1 times the monomial basis, and that is 1, t, and t squared. Okay, now I've multiplied everything out, and I write it in matrix form. Okay, so this is in Bernstein. In Bernstein form, because the polynomials, the basis polynomials here are these Bernstein polynomials, and now I write the whole thing using my monomials. Okay. Now I use the monomial form. Monomial. Then I just say my curve, C of t, it's the same curve, right? C of t, it's the same curve. But I write it differently. I write it now, I from 0 to 2 of bi bar, I don't know these guys, bi bar, times monomial basis. And the monomial basis is always t to the ith power, right? The most primitive basis there is, right? T to the 0, t to the first, t to the second, and so forth. I write this out, I spell this out. So this also in matrix form would be a row, B0 bar, B1 bar, B2 bar, times, and now it's just the monomials that follow, This is 1t and t squared. Okay. And now this curve is the same as this curve, so that means I just set these expressions equal. I set that equal to this, and the unknowns are the coefficients for a monomial representation. So I get B0 bar, B1 bar, B2 bar equals, what did I do? I set this expression equal to the one on the bottom of that side. Okay, so I can forget about this part because it is the same. You believe me that I can ignore that. And then I have the result. The unknown B bar control points are just the original Bezier control points times these coefficients. So that is then 1, minus 2, 1, 0, 2, minus 2, 0, 0, 1. The original points come in front of it. Original points are B0, B1, B2 times this coefficient matrix 1, minus 2, 1, 0, 2, minus 2, 0, 0, 1. And that's it. And these are the guys that I want to solve for. Now, is it all clear again why I did this? No, we have forgotten the whole purpose, right? I was dwelling and was getting into details. So let's forget about the detail. Let's try to understand again what I was after. I was after a very efficient scheme to compute points on the curve. I said the original de Castillo algorithm, even though it's beautiful, it is expensive. It's quadratic in time. I don't like that. Therefore, I would like to be able to evaluate it in linear time. Can I do that? And then I put this beautiful scheme here on the board where I took t out, right, and so forth. And I said I can evaluate a curve in linear time if I have it in monomial form, if I use as basis functions the powers of t, and only the powers of t. So therefore, then the question arose to take a Bezier curve defined in terms of original Bezier control points and Bernstein polynomials in terms of the monomial basis. Okay, so I'm given the original Bezier polygon, the Bezier points, and I want to convert it to a representation where I express the same curve using powers of t. So then the unknowns for this representation are the coefficients in front of the powers of t. And that's what I did. And when you figure it out, well, all you need are these new control points. You can think of them as control coefficients. They no longer have this beautiful geometrical point interpretation. You have these new coefficients, the bar guys, and they are related to the original control points, which you know by a coefficient matrix. And this coefficient matrix comes from multiplying out the Bernstein polynomials. That's it. Okay, now we can spell this out for arbitrary n, and that's in the book, and I don't want to do that. All right, so that means you can take any curve, polynomial curve, given to you in Bernstein form, Bernstein-Bezier form, and convert it to a monomial expression for the purpose of accelerating the evaluation. Shoot.
So it seems like you're taking the complexity out of doing the Castillo and doing a matrix multiplication instead. And is that really a lot better? Like, say you just wanted to add another point to your Bezier curve. You have to recalculate your B-bar coefficients.
You need this relationship between the new B-bar coefficient and the old coefficients, right? Very good question. When is it worthwhile to worry about doing this transformation of? Think about that. There's a break-even point when it's worth doing that, and when it's not.
That's change of basis.
No, they are not. There are many, many other aspects about the beauty of the Bernstein basis, why it's a beautiful basis. Okay, it's numerically stable, it's intuitive, and all kinds of stuff. It's a partition of unity, and all of that. But nevertheless, if you have to get to the ultimate performance, you have to do this. Okay? When it comes to high order curves, even though this scheme sooner or later becomes numerically unstable relative to the Bernstein basis, but that's a separate topic. But you're thinking about a very good topic, namely how expensive it is to to have these coefficients computed for the matrix and then doing the multiplication. Okay, so the question then are, how often do you have to do this and so forth. That's a good question to think about at home. So change of basis. Let's see what the next topic is I wanted to talk about. Degree elevation. I want to talk about degree elevation. What is degree elevation? Who has already looked at the book a little bit? Degree elevation.
Just increase the number, so you make a curve that's order 3, order 4.
That's it. Or degree 3, right? Degree 4, right? Degree elevation, order elevation. People just focus on degree, okay? The degree of a curve is always one less than the order, right? Right? So, degree elevation. So, I take the degree, this is number n, and elevate it, make it larger. Why do I do that? It's not quite clear yet, right? So I talk about the purpose, why people worry about that at the end. But first I talk about the recipe, how to do degree elevation. Okay? Degree elevation. The issue is, let's go to our little ideas side of the board. If I give you a function, f of t, that is 1 plus t, then the degree is, give me a number, 1, because the highest power of t is 1, okay? All right. Do you believe that this function is the same as this function? It's 1 plus t plus 0 times t squared. So what is the degree of this function? But it has 0 in front of it. So this doesn't really count either. That's the trick that we play with the Bezier curve. Okay, this was the analytical way of looking at it. Okay, you are confused now, right? That's good. Now I also say I give you a very simple Bezier curve. I give you a Bezier curve of 2 points, defined by 2 control points. What is the Bezier curve defined by 2 control points? That is the line connecting them, right? Right? Okay. Okay. So this is a curve that is of this form, right? And power of t is in there. Okay. What? So this is B0. And this is B1. Okay. Now I give you a Bezier curve that has 3 control points. I give you another Bezier curve that has these control points. Big circles. Circle 0, circle 1, and circle 2. So that control polygon has control points B0 bar, B1 bar, and B2 bar. Okay. What is n for the first curve on the right, which are the small circles? What was n here? That was n equals 1, right? Because the curve defined from this side was sum I from 0 to n, it's 1, of the original bi times bi1 of t, right? But on the other side, I gave you 3 control points, defining obviously, just follow your intuition, the same curve. But it's defined in terms of 1 to 3 control points. So the curve there is I from 0 to 2, bi bar times bi2 of degree 2 of t. So what? I confused you there, I confused you here. A line is a line, right? So but any line is also a parabola, right? So the general parabola has become a straight line. So this is what we do. We take something of low degree, i.e. something like a line, and lift its degree up to represent the same thing in terms of 2 control points with 3 control points, in terms of n control points to a curve that has n plus 1 control points. And all I'm doing is now give you the geometry how to do that. But before I come to the geometry, we have to do the analytical derivation. What is ultimately the beautiful geometry to do then? Here it was intuitive, right? If I give you the control polygon for a line, of course, intuitively you know that the quadratic representation of that is this point, the midpoint, and that point, right? It's clear. But how do you get n plus 1 control points from a more complicated polygon, right? That's what I'm after. So how do we do that? And at the very end, I talk about the purpose, why we even worry about that. By the way, you always have to ask about purpose, right? No matter what you learn, right? No matter what algorithm, no matter what technique. Whenever you learn all these little recipes and these algorithms and this and that, you always have to go back. And first you have to fully understand what the thing does, the algorithm or the method, but then you have to step back and ask, why? Right? Why do we do this? Purpose. So we come back to that. All right, so degree elevation. Degree elevation is also change of basis. We go from a basis of degree n to a basis of degree n plus 1. So it goes back to the topic that I just talked about, degree elevation. Degree elevation for Bezier curves. And we develop the formula or the beautiful geometry via a change of basis. And I do the example that I did here, n equals 1, because it gets very complicated very quickly, okay? So example, n equals 1. Okay, so what do I want to do? I want to represent the line as a Bezier curve of degree 1, and I want to represent the same line as a Bezier curve of order 2. And I want to understand what the relationship between the control points are, or control points is, right? So I start with this curve, which is given. So given to me this representation, I have a curve, Bezier curve, C of t. Very simple one, just two control points, I from 0 to 1, bi 1 of t. Okay. Now, again, I go back to this representation using matrices from a while back. So I also can write this as a row b0 and b1 times the linear Bernstein basis function. They are very simple. It's just 1 minus t and t. And I further multiply that out. So then I have b0, b1, and I write this in monomial form. So then this becomes 1, minus 1, 0, 1, and now a column of monomials, 1 and t. And now comes the trick. Can I also write this with a quadratic term in there? Yes, plus 0 times t squared. Right? So that is, this plus 0 times t squared will not change anything about the curve. So I add plus 0 times t squared. If I do that in matrix form, then I would say this is b0, b1 times 1 minus 1, 0, 1. And now I say plus 0 times the t squared term. So now the column vector here is 1t squared. But in the end, the t squared will not play any role because that will be multiplied by 0. Okay, so that is the trick. Now I have shifted from linear to quadratic. Well, it looks quadratic even though it's still a line. So this is still linear, or degree 1 here, and now it has become degree 2, right? Because of the quadratic term which we have added, that we multiplied by 0, so it doesn't really have an effect. And now we want to find out, well, if I'm given the original control points, B0, B1, how do I represent the same curve with 3 control points? We already know by intuition where they are. They are here, right? One is here, one is at the middle, and the other one is here. Those are the control points for the same curve using n equals 2. So B0 bar is unknown, B1 bar is unknown, and B2 bar is unknown. So now I write the same curve using degree 2 basis functions. And then I have to set it equal, and I solve for the unknown bi bars. So now I also say C of t is also sum I from 0 to 2. That's the trick. And I do not know the control points for that one, bi bar, bi2 of t. And I multiply it out. When I multiply it out, boom, 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 I get, in the end, the row of the unknown bi bar coefficients or control points, b0 bar, b1 bar, and b2 bar, times, now comes the coefficient matrix for these quadratic Bernstein functions, Bernstein basis functions, and that was 1, minus 2, 1, 0, 2, minus 2, 0, 0, 1, times 1 t and t squared. Okay. If this curve is still the same curve as that, then I set these things equal and solve for the unknown bi bars. That's the trick. Okay. So these are the unknowns. Unknown. And so this is expression 1, this is expression 2, and I set them equal. So when I do that, 1 equals 2, from that follows the relationship, and the relationship says that the unknowns, b0 bar, b1 bar, b2 bar, times this coefficient matrix, 1 minus 2, 1, 0, 2 minus 2, 0, 0, 1, equals the given points, b0, b1, times a 3 by 2 matrix, 2 by 3, 1, minus 1, 0, 0, 1, 0. Okay, that's the relationship. And I already have omitted these terms, right? I don't need to worry about them because they appear on both sides, so I can ignore them. Now I have this equation. What I'm after is the bi bar, so I solve for that. So I can just say this is a matrix. I just call this matrix M. Okay, and I call this matrix also M. Well, I should give one the name bar because this matrix goes with the bars. I call this matrix M bar. Okay. So these are the unknowns. So then I can just say the unknown control points B0 bar, B1 bar, and B2 bar are simply, now I bring this M bar matrix over by taking its inverse and putting it on the right end, right? So then this is just B0, B1 times M bar inverse, M bar minus 1, right? So that guy is the inverse of M bar. And then I've solved it. Now for this particular example, you can do that at home, okay, and actually solve it, do that. You only have to deal with 3 by 3 matrices, so that's still simple. I give you the result that comes out when you solve this with you do it with Mathematica. Okay, Mathematica can be helpful, whatever you like in terms of a symbolic solver. When you solve it, of course, you get what we see by intuition. By intuition, we see that the B0, B1, B2 bars are related to the original B0, B1 in this way. Right? The two endpoints are the same, and then B1 bar is the midpoint of the original two control points. That's what comes out when you actually solve the system. That's what you get. So when you solve it, solution. When you solve this, you get B0 bar is B0. You get B1 bar is the midpoint, or 1/2 of B0 plus B2, B0 plus B1. And the last unknown point, B2 bar, is B1. That's what you get when you solve the system. And that's, of course, your intuition, right? Now, everything that we do with these Bezier curves is quite nice in terms of the geometry. And also, this degree elevation business becomes very simple when we look at the geometry that is involved. Now, for the linear case, for the line, it was very simple. We took a line and the new control point was the midpoint. Now, is it equally simple for the higher order or the higher degree curves, where we can have a geometry, a pattern that we can remember? I mean, I put all these formulas on the board and all these matrices, right? That's just the analytical derivation of a beautiful geometrical construction. All that I want you to appreciate and remember in the end is what I put on the board, the geometrical construction. The rest was just an analytical derivation and analytical justification of what this geometrical construction does. So now it all leads to a beautiful geometrical scheme, leads to simple, I call it, simple geometrical construction. And, well, n equals 1 we did. So the next example is I give you the case for n equals 2. I give you a configuration like this, a curve defined in terms of 3 control points, B0, B1, B2. And I want to represent the same curve, this curve, using 4 control points. Where are the other 4? Okay, so these are given. The unknown, obviously, are then B0 bar, B1 bar, B2 bar, and B3 bar. Okay. We want to go from 3 to 4, and we give them bars. And they will be combinations. I think I said earlier on, the only thing that they need to understand in this class is linear interpolation. Okay, so each of these new control points will be combinations of the original ones. And this is just the result when you solve the particular system I put in the board for the general case. So the first one will be something times b minus 1, something times b0. It's all about patterns, right? Something times b1, something times b2. Okay, these are the original points. b minus 1, b0, b1, b2. What's he talking about? b minus 1 doesn't even exist, but he has to put it there because for formal reasons. Okay, the formula requires it. Plus something. This is a linear interpolation step. So this goes up the index from minus 1 to 2. So here the index is something times some other control points, b0, b1, b2, and b3. What is he talking about again? We don't have a b3 to begin with. Where does it come from? Okay, so really these things are undefined, so put them in brackets, okay? But the others are defined, right? These are the original creatures. And so now I just give you the formula. We divide everything by 3 because we go from n equals 2 to n equals 3. So we are dealing in thirds. And then we start, well, this one doesn't have a meaning, doesn't mean anything, it's undefined, so therefore we better give it the weight 0, right? This thing, B3, doesn't have any meaning, so we better give it the weight 0. Okay, now this 0 has to go up from 0, 1, 2, 3. Pattern, 1, 2, 3. And here it goes probably from 0, 1, 2, 3 that way. Okay, it's all about pattern. Okay, so what does this mean? What does this mean? B0 bar is what? B0 bar is nothing plus 1 times B0. So B0 bar is B0. Okay. The other part that makes obviously sense right away is that the B3 bar is the old last point, B2. So this guy here is also B3 bar. And this one is B0 bar. So we need to understand where these points lie. And they are linear combinations of two consecutive original control points. B1 bar is a combination of B0 and B1. B0 and B1. B0 and B1 define this line segment. And then these fractions in front of them define the way how we split the line. It's 1/3 times B0 and 2/3 times B1. That means this point is closer to B1 than it is to B0 because B1 has a higher weight, 2/3. Okay, where do these weights, where are they reflected? Well, the ratio is 1 to 2. Something is split in a ratio 1 to 2. The line segment is split in a ratio 1 to 2. 1, 2, 2. 2 to 1. Then the next one is the same thing. B2 bar is a combination of B1 and B2, so it must lie on this line segment. And we split the line in a ratio 1 to 2 here. So here we split the line in a ratio 1 to 2. Okay, so the polygon that we are after is this new polygon. So this is B0 bar, and this is B1 bar. And the new polygon is this guy. Now we have two polygons that, when you evaluate them, give you the same curve. Okay? And all that we need to remember here is these ratios. Okay? We started with n equals 2, and then we started subdividing things in certain ratios, right? 2 to 1, 1 to 2, and so forth. I will do an example then for n equals 3 and n equals 4, and then you will see that even more intuitively. But from this, you also see the formula that can be digested by the machine, right? The machine likes the formula in terms of a general variable I. What is the formula that we need? We need to write the arbitrary formula for how one of these guys is related to two given guys, right? Do you see that? So what is the formula? The general formula. The general formula is on the left-hand side, we have an unknown, bi bar is related to I minus 1 and I, right? One index is related to 0 and 1 index, so there is something in front of it times bi minus 1 plus some ratio times bi. Okay, so what is in front of it? What are these ratios? So here we had n equals 2, and we had to divide by 3. So that 3 is n plus 1, right? So we divide by n plus 1, n plus 1, n plus 1. And what are these numbers? So B0 bar, the 0 goes with the 0. B1 bar goes with the 1, so that's I, obviously, in the numerator. I. And here, what happens here? Here, it's 0, and we start with n plus 1, and then it goes down by 1, right? So we start, 0 goes with n plus 1, and then it goes down. So that means here we have n plus 1 minus I. So that's the general formula. A very simple formula that the computer likes. And I, we have to tell the computer I from where to where. I goes from 0 to n plus 1, right? And we also have to tell the computer that this guy, whenever it is trying to do something, is 0, or it's a 0 vector, or the 0 point. And this also is 0, right? This guy is 0. Comma, where this b minus 1 is defined as 0, and b n plus 1 is also not given, so you have to set it to 0. That's the formula. So now to become more fluent with it and more able in terms of using it, based on geometry, I give you the other cases, from n equals 3 to n equals 4, from n equals 4 to n equals 5, and so forth. So now we do from n equals 3 to n equals 4. Okay. Now I do not put any formulas on the board. I just think in terms of the geometry. That's all I need to remember. So I start with 3. N equals 3 means the control points are B0, B1, B2, B3. And now I want to go from 4 points to 5 points. Where are they? Okay. Where are they? The 3. Any idea where they are? Where would they be? What ratios do I have to use? What ratios did I have to use here? Here I had to deal, that was 2, and I was going from 2 to 3. The ratios I had to consider was 2 to 1, 1 to 2. So what are the ratios I have to consider there? 3 to 1 and 1 to 3. That's one ratio I have to consider, yeah? So the first intuition is the endpoints still coincide, right? Okay, before we worry about the ratios, how many control points do you need? How many more squares? 3 more. Follow your intuition. Where would they lie? One would lie probably on this line segment, yes, because each new control point is a combination of 2 old ones, right? One has to be here, one has to be here, and one has to be there. Okay, follow your intuition. The one at the middle line segment probably has to lie where? In the middle, okay, yes. And if we do that, we have to find ratios for what number? For this number, 4. This is 2 to 2. Okay? This ratio is 2 to 2 or 1 to 1. The other thing is here, and that was your ratio, 3 to 1. And the other one lies here. That's that ratio, 1 to 3. 1, 2, 3. So these are different, these ratios, the integers sum to 4, right? 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4. That's the way, that's the pattern. Now we have the pattern, right? So this is B0 bar is B0. This is B1 bar. This was B1. This is B2. This is B3. And B3 is also B4 bar. And this guy is B2 bar. And this guy is B3 bar. Okay. So now the new control polygon is this guy, connecting all the squares. And again, both polygons will lead to the same curve. Now if we can go from 3 to 4, now we can also go from 4 to 5, and then I will stop, right? So I make a very beautiful picture from 3 to 4. The next one, I sketch even less. The next one is from, it was from 3 to 4. I say from n equals 4, we will go to 5. From n equals 4, we go to 5, n equals 5. So n equals 4 means 0, 1, 2, 3, 4. These are our originals, right? Okay, there we had to use fourth, divide the line segments into 4 pieces. Now we go to 5, meaning we divide each line segment into 5 pieces. Each line segment is split into 5 pieces. 1, 2, 3, 4, 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 5 pieces. Okay, the new control points are circles. So the circles are the old ones, and the squares are the new ones. And at the ends, they agree. And now in between, I have to play the game with how can I decompose the number 5 into 2 integers, right? So it's 5 plus 0, 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4, 0 plus 5. Those are the ratios, okay? So the next one goes here, because that's the ratio 4 to 1. The next way to split the number 5 is 3 to 2. This one here. This is 3 pieces there, 2 pieces there. Then comes 2 plus 3, 2 to 3 ratio. And the last one is this guy, 1 to 4. Okay. So the new polygon is this polygon. And when you evaluate it, it's the same curve. So this is the only thing you need to remember. Okay? That's the only thing. Okay, here's 5, and therefore you have to worry about how to split the number 5 into different integer combinations when you sum it up. That's it. That's all you need to remember. All the rest that I had on the board was just a lengthy derivation of all of that, right? And more of that is in the book. Is anything not quite clear, or is this crystal clear to everyone, or? Shoot. Make sense? Whenever something doesn't make sense, or I make a mistake, jump in there, okay? So now that we know how to do this, we have to worry about, well, he has talked about all this stuff, this degree elevation, it's a beautiful pattern and so forth, and I can appreciate that, but why do we do that? Why do I even worry about that? Why do I worry about that? I worry about that for 2 reasons. Why? Right? Why do I do something? It's a big question. Why? Why degree elevation, right? Why do I do degree elevation? Reason number 1, I have a computer-aided design system that only allows me to use cubic curves. You may have heard that cubic curves are the standard, right? Cubic, 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 that is n equals 3. Right? So if you have a standard and your system requires you to only operate on cubics, i.e. default is n equals 3, and it only allows you, then you have to translate everything into that, right? So it has to do with standards and data exchange. You have to convert things, right, into something that might be of higher degree. Standard, or compatibility with a system that supports only a certain degree of a curve, no matter what. Compatibility with a system, a design system supporting only a specific degree n, supporting only a specific degree n. But the more important reason is this one, and that has to do with the later use of the curves for construction of surfaces. Okay? Surfaces constructed from curves. Okay, and I give you an example. That is a so-called ruled surface, a ruled surface. Ruled surface works as follows. I give you one curve, and I give you a second curve, and then I connect corresponding points on those curves to get a surface in between. That's ruling. Okay? So a ruled surface works on this principle. I give you a curve number 1, I give you a curve number 2, and the surface that is implied by those, or that I construct, is defined by connecting corresponding point pairs. Okay, so that is the surface that I construct here. Okay. Okay, a curve number 1 and a curve number 2. The way I've drawn the curves, they are different, right? The first one probably is a parabola, and the second one obviously has an inflection point. You need n equals 2 for that, you need n equals 3 for that, right? Quadratic and cubic. So here, you probably have a control polygon that looks like this. It's good enough. But here you need a control polygon that probably looks like this. Right? So now there is an inconsistency. Right? You probably have an intuition that when you want to deal with surface schemes, the one that only has 3 control points as a boundary curve that is to be connected to one that has 4 control points, this one probably has to be lifted or degree elevated to something that also has 4 control points. Can we do that? Yes, we know how to do that now, right? Now we can do degree lifting or degree raising or degree elevation and represent that curve with 4 control points, right? And then we have consistency there. One curve, 4 control points, second curve, 4 control points we can connect. Okay? And again, will become much more obvious when we talk about how to use the curves to construct surfaces. Need same degree curves for many surface operations. Same degree curves for many surface constructions and representations. Constructions and representations. And more later on that one. Okay. Maybe I should conclude with one more important property of a Bezier curve. What were the important properties that we talked about so far? What is true about a Bezier curve? Given the control points of a Bezier curve, B0 up to Bn, the Bezier curve always satisfies the following conditions, facts, properties. What is it?
The first must be like the endpoints of the curve. The first must be
B0 and Bn are the endpoints of the curve. What else? Convex hull, the curve C, lies entirely in the convex hull of its control points, and therefore it lies in the bounding box of the control points. What else?
the last one in the bounding box, which follows directly.
Yeah, we did that. There's another one which is called the variation diminishing. The variation diminishing property. I just want to bring it up because you will see it in all these papers and also in the book. Variation diminishing. Variation. What is variation? Variation, varying, to vary around, to oscillate, probably has to do with how wiggly such a thing can be, right? The control polygon has a lot to do with the behavior of the curve, right? So therefore, when we talk about variation of the curve, maybe the control polygon gives us an indication of how wiggly or how varying a curve can be. Okay, so, and yes, indeed, that is called the variation diminishing property. Variation diminishing property of Bezier curves. All right. I give you, and all I have time for right now is to sketch the basic idea. I give you this polygon, and I tell you the curve that is implied by this polygon is this one. Can that be? No, that cannot be. Why not? It violates many things. It violates, like, it's outside the triangle, the bounding box. So this can really, violating many things here, okay? Can't do that. How about this? It stays in the bounding box and convex hull property. I say this is a curve. Probably not. And this goes at this idea of variation diminishing. The curve cannot be more wiggly than the polygon is. All right? So these 3 points always define a convex configuration. That means the curve can only be convex. It cannot have an inflection point, not a single one. Right? So it has to be a parabola. Its general shape has to be somewhat like this, right? It has to look like that. And the wiggliness can be measured by an intersection test. When I consider all possible lines that I construct, how many intersections can I have maximally between all possible lines and the polygon? How many intersections can I have maximally between a line and the polygon? How many? 2 at most, right? I mean, here I have 0. When I go to the vertex, it's 1. But at most, 2 intersections. So the maximal number of intersections I can have between the set of all possible lines and a polygon is 2. Then the curve cannot have more than 2 intersections with the entire set of all possible lines. And all these curves, indeed, have at most 2 intersections, right? So here's a parabola. And yes, also these guys can have at most 2 intersections with all possible lines. Okay. That means when I have a polygon like this, how many intersections can I have maximally between any line and the polygon? How many? Maximally. 3, because this is, for example, one of those lines that produces the maximum number of intersection points. 1, 2, 3. That also means that the Bezier curve implied by the polygon must have a shape that cannot have more than 3 intersections with any line. So, well, this is the curve, right? And indeed, when you consider the set of all possible lines, this is one line that leads to the maximal number of intersections, 3. The curve must not wiggle around more than the polygon does. Okay. So the important insight here is curve cannot have more intersections with a line than the control polygon has. This also has another implication, which is a byproduct of this. If I give you a convex control polygon, then the curve has to be convex. Okay? So if I give you a convex polygon like that, then you have a convex curve. Because a convex polygon can have only 2 intersections with any line. Therefore, the curve also has to be convex. Okay? So if I give you a convex polygon, then the curve also has to be convex. Right? Convex polygon at most 2 intersections with any line. Therefore, curve also has to be convex and can have at most 2 intersections. Okay. So, and again, why do we worry about this? We come back to that later. Why this variation diminishing property is interesting. See you on Tuesday.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.